Hi everyone, my name is Lingzhi, and today I'd like to show you some ice and soil mixtures, which we modeled using the two-layer radiative transfer model. So we already know that the permanently shaded regions near the lunar poles have a surface temperature that can be lower than 110 K, which supports the presence of water ice. And the spectral absorption features have been detected using the M-cube dataset. However, the state or the presence form of the water ice is still sort of unknown. They can be frost, ice patches, or ice boulders. So in this work, we present several possible states of water ice and soil mixtures. The first one will be a very simple linear mixing between ice and soil grains. The second one will be slightly more complicated. So we included 6 cases of two-layer mixing, including ice frost over soil or rock, and ice patch over soil or rock. And the last one is soil over ice frost or ice boulder, because later impacts can lay a thin layer of soil over these ice features. So we modeled the water ice spectra using the optical constants derived by Warren and Brent in 2008. So on the left, we have a example spectral modeled from the optical constants, and the wavelengths we're using varies from 0.5 to 2.6 microns. And we have a series of spectra having a grain size variation from 50 to 400 microns. And you will see that most of the spectral features increase in depth with increase in grain size, which is consistent with the measurement of water frost by Clark 1981. And let's start with linear mixing of ice and soils. So we present 2 examples. One is orthopyroxene mixed with ice, and another is ornostatic norite mixed with ice, because the South Pole lichen is sort of dominated by orthopyroxene as a mafic mineral. So from the red is pure soil, and dark blue is pure ice. And in between are the mixtures of the two, varies from 0% to 100%. You can see that most of the small features of the ice at 1.0 and 1.25 sort of disappear, and the soil content increase. But those absorptions at 1.5, 2.0, 2.5 microns still have a relatively deep absorption, even there's only 10% of ice involved. And also, when there's only 10% of soil included in the mixture, the 0.9 also pyroxene absorption is still kind of significant in there. And I'd like to introduce a little bit about the model itself. And this two-layer model is from the Hapke book. It consists of 2 layers, obviously. The upper layer is optically thin. It can be either powders or slab, and the lower layer will be an optically thick material. And the thickness of the upper layer can vary, but it has to remain in the optically thin range. Then you can calculate the reflectance using these equations, which you can find from the Hapke book and also in our earlier work. And in this work, we modeled the upper layer, we let the upper layer thickness to vary between 30 to 60 microns. So we'll have 4 mixtures of the two-layer spectra. We use the same mineralogy for soil and rock. And we used a 90 magnesium number ornostatic norite composition, because South Pole lichen. Yeah. Then to mimic the space weathering effect, we added 0.5 mil nanophase iron, which is slightly, because the rock will be slightly more immature than soil, but to simplify the case, we just use the same nanophase iron amount for both. So the first result will be ice frost over soil on the left and ice frost over rock on the right. So the red spectra is pure soil and the black spectra is pure ice. Then from light blue to darker blue shade are a series of two-layer mixtures with the upper layer thickness vary from 30 to 60 microns. And you will see that at the shorter wavelengths, the smaller absorption features of ice kind of disappeared. You'll only be able to see the 0.9 micron absorption from orthopyroxene. But still the 1.5, 1.6, 2.0, and 2.5 absorptions are quite deep, so it's pretty obvious for detecting ice using these features. And also the overall reflectance of the two-layer spectra will be higher than the pure soil. And in the case of ice frost overlying rock, because rock spectra will be darker than soil because the stronger forward scattering. And in this case, the modeled two-layer spectra is still brighter than the pure rock spectra itself, but darker than the ice spectra. And the second case is ice patch or soil or rock. So we modeled this because ice patch may not be covering the entire surface. So only 50% of the surface will be covered by ice patch. And in this case, you will see the spectra, the blue spectra, which is the model two-layer spectra, are dominated by ice features, plus that 0.9 pyroxene absorption. And in this case, when there's ice patch overlying the soil, the shorter wavelengths will show a much higher reflectance compared to ice. While in the case of rock, the two-layer spectra will be kind of similar or even lower than the ice in the shorter wavelengths in reflectance.
1 minute left.
Okay. Then in the case of soil overlying ice, frost, or boulder, we'll see that still the spectra feature is dominated by ice absorptions plus that also pyroxene absorption at 0.9. And the overall continuum of the two-layer spectra will sort of being less blue than the ice itself. And in the two cases, when soil overlying ice frost or soil overlying ice boulder, the modeled spectra look kind of similar. And here's my conclusion. We modeled 6 cases of ice and soil or rock mixtures using two-layer modeling, but this work still need validation from lab simulations. If we want to quantize the content of water ice or water ice patches, because the determination of the thickness of these frost or thin patch might be a little bit challenging in lab, but this will be very useful for estimating the amount of water on lunar surface. This two-layer model can also be applied to model the mixture of soils and other ice types. For example, methane and carbon dioxide, as long as their optical constants are available. And that's all I have. Thank you for your time.